Okay, hi, what's up? So we go to our next lab now. So, okay, next lab is going to be about the Hubble Law, one of the most important laws in astrophysics, and the law that led to us believing in the Big Bang Theory. Okay, most galaxies appear to be moving away from our own. Furthermore, the recessional speeds of the galaxies are proportional to their distance from us. This is what came to be known as the Hubble law. Velocity of recession is proportional to the distance of the galaxy from us, and the constant of that proportionality is h, is known as the Hubble constant or the Hubble parameter. This law discusses the Hubble law, shows us how it can be used to estimate distances to remote objects, and illustrates that the law is a consequence of the expansion of space itself. Okay. So the constant describing the rate of this recession is called the Hubble parameter. It's used to determine the age and the size of the observable universe. So the Hubble parameter, which often is also called Hubble constant, is used to determine so many things like the distances of galaxies from us. It can be used to determine the size of the observable universe and even the age of the universe. The Hubble parameter h indicates the rate at which the universe is expanding, and thus can be used to estimate both the universe's size and age. Therefore, it is very important to determine an accurate value of the Hubble parameter. Note that h has the units of velocity divided by distance. The value of h is usually quoted in kilometers per second per megaparsec. Different units will be used for the values of h contained in the two exercises later in this lab, but the units will still be those of velocity divided by distance. There is still some uncertainty over the exact value of h, but most current estimates lie around 71 kilometers per second per megaparsec. For calculations in this lab, we shall use the value h equals 65. So we've seen that before in a couple labs where we needed to use the h value. And I guess for these labs, they're using h is 65 as the default value. Adopting this value for h means that for each megaparsec of distance, the velocity of a distant galaxy appears to increase by 65 kilometers per second. For example, using the Hubble law, we would expect that a galaxy at a distance of 2 megaparsecs from Earth would have a redshift corresponding to a radial velocity of 130 kilometers per second. So essentially, it's just a simple math. You just have v equals hd, and then if your h was 65, then you just multiply that by 2, and then you get 130 kilometers per second. So redshift exercise. So for each of the galaxies in the table below, calculate the distance from the given radial velocity. Distance from this given radial velocity. For this exercise only, assume a value for the h parameter, 67 kilometers per second per megaparsec. Record that Hubble law is v is hd. So if the radial velocity is 231 kilometers per second, so they want you to solve for d in this equation. So you basically divide v by that h value, and then you get units of megaparsec. So you can show work for these four. It's pretty straightforward calculation compared to other calculation that you guys have done. This is like nothing. So you essentially just divide this number that they gave you in kilometers per second by this, and the kilometers per second cancels, and then you get megaparsec that comes out. So then you show the work for these and also take a snapshot of your result. Which of the following statements is not true? And then answer these, and again, take a snapshot of that. Oh, okay, that's it for that part. Okay, then you have quasars and Hubble law. So they've referred to the term quasar before several times during these labs. So let's see exactly what is a quasar. Very bright and very far. Quasars are very distant objects, which means that if we can find the redshift parameter, we can use Hubble's law to find out how far away they are. So they're very distant galaxies, actually. So quasars are very distant objects with large redshifts and enormous luminosities. They are an extreme form of the active galactic nuclei and are powered by rotating supermassive black holes. So that's going to be one of the extra credits that you will do if you want to do them, that you're going to do active galactic nuclei. These are very active nuclei of very active galaxies. And quasar is an example of a very active AGN, active galactic nuclei. And they're powered at their centers by their supermassive black holes. Quasar 3C273, shown above in false X-ray color, was the first quasar identified and is the brightest and nearest quasar known. Interesting. So this is the first quasar, is the brightest and the nearest quasar to us. This view shows us a part of a relativistic jet, lower center. You see here, this is the lower center, being ejected by the central black hole engine located in the core. So it's emitting a huge power of X-ray jet. Since quasars are very distant, we may expect that Hubble's law should apply to them and that their redshift should depend on their distance. In the exercises that follow, we shall see how to determine the redshift of a quasar and learn how to use Hubble's law to relate the redshift to an approximate distance for that quasar. So spectral lines. The spectrum of a quasar is not determined by its temperature and thus is considered non-thermal spectrum. So this is interesting. So it's basically not determined by the temperature of the galaxy, the spectrum of the quasar, and therefore is called non-thermal. Non-thermal, a spectrum which lacks the characteristics of a black body radiation and is not dependent on the temperatures. However, we can still determine the quasar's redshift from the position of emission lines within that non-thermal spectrum. The spectrum of an object is formed by separating the light that comes from it according to the wavelength. For individual stars and galaxies, one typically sees a thermal spectrum marked by some number of sharp absorption and emission lines, like the lower spectrum in the figure. So it says here, for a normal galaxy, the frequency of the spectrum, and then this is the relative units, the flux, the intensity. So this is the normal, this is called the black body curve for a spectrum. And I believe we had a lab on that, right? Yeah, we talked about the peak wavelength that it peaks at. It was called Wien's law, right? So it was the frequency. Remember how we said hotter objects emit more light towards the lower end of the frequency, the higher end of the, we said, excuse me, higher objects have a peak towards the higher end of the spectrum. So this is the Wien's law graph, but then this is the spectral emission of quasars. This is near infrared, so it's lower frequency. This is the visible spectrum, near infrared, far infrared, and then radio frequency. And then, of course, they're not showing us here the X-ray, the UV and the X-ray would have been on the left side here. So this is showing only the visible spectrum and then shorter frequencies, smaller frequencies. Near infrared is near the visible, far infrared, and radio. So it seems like quasars are dominated in the far infrared. They emit a lot of heat. Also some near infrared, but not too much visible. You see, their intensity in the visible is low. So they're very hard to see. Very, very hard to see, but a lot of infrared and heat. So we could study them using infrared telescopes and also radio frequency. On the other hand, the spectrum of a quasar is very different from that typical stars and normal galaxies. It does not show the characteristics of a blackbody radiation spectrum and is termed a non-thermal spectrum. Quasars and active galactic nuclei have non-thermal spectra like the upper one in the illustration. Many quasars also have broad emission lines superimposed on their non-thermal continuum of radiation. So it's very weird, different looking spectra. Broad emission lines. The position of these lines allow the redshift of the quasar to be determined. Determining redshift. Using the emission and absorption lines that are well known on Earth, we can calculate the redshift parameter by comparing these lines to those visible in a quasar's spectrum. To find the redshift, so we've seen the redshift before, but we haven't actually seen how to calculate it. So this is going to be the first time that we see the calculation of the redshift, the Z value that we've termed before, Z. So it says, to find the redshift, the spectrum of the galaxy is taken using a telescope and a spectrograph. The function of a spectrograph is to sort the incoming light by a wavelength, then produce a graph that shows the intensity of light at each wavelength. In this case, the spectrum is shown as a graph where peaks represent emission lines and valleys represent absorption lines. So you see the peak represent emission line and valleys represent absorption lines. The redshift equation is lambda prime minus lambda over lambda. So in other words, how much the wavelength has been shifted, the new wavelength, lambda prime, minus the known wavelength that it should have if there was no redshift, that would be lambda, divided by the lambda. Lambda prime is the shifted wavelength of the peak, lambda is its corresponding rest wavelength, and z is the redshift. The units of wavelength used here is the angstrom, equal to 10 to the minus 10 power. So that is meant to be 10 to the power negative 10. The equation below the graph gives the correct redshift of the galaxy when the red line is aligned with the magnesium. So it says here, the equation below the graph gives the correct redshift of the galaxy when the red line is aligned with the magnesium 2 peak. In real redshift measurements, calculations like this are done for every identifiable peak, and an average is taken to find the best value for the redshift. Okay, so then let's look here. This is a plot of the relative intensity of the galaxy versus the wavelength. Click on the plot to fix the wavelength of the wavelength. Okay, the formula below will show you the corresponding value of Z, given that the rest wavelength is 2798 angstroms. Oh, okay, so they're focusing here on the magnesium, the redshift determined from the magnesium 2 line right here. Let's see here. Oh, I see. Let's see, where's the magnesium 2 line? Redshift determined from the magnesium 2 line. The formula below will show you the corresponding value of Z, given that the rest wavelength is 2798. Hold on, let's see, 2798. This is a huge shift then. Hold on. So this is the H gamma. This is the hydrogen bomber line, H beta. Remember, there were 4 hydrogen bomber lines. We can't go beyond the scope here. So let's see here. So you go to the magnesium line. Here's a peak right here, the magnesium line right there. Redshift determined from the magnesium 2 line. You should find that the position of the magnesium 2 line indicates a redshift of about 0.51 for this galaxy. So how are we getting that? Let's see here. There's no play button. I guess, yeah, basically. So it's like 4212 is the one, is the wavelength that it's showing. That's a huge redshift, minus 2798 over 2798. Let's see if that's what we would get. See, if we change this, it's not changing with us. It would have been nice if this number changed. Let's just put it here. Let's see what we get here. Right there. 4223. Okay, so let's go to 4223 minus then we have 2798 equals, and then you divide that by 2798. Oops, hold on. 4223 minus 2798. 4223 minus 27. You know what I should do? Hold on. Let's do this. 4223 minus 2798, close parentheses, divided by 2798. 0.509. Yeah, that's 0.51. So that's how they're getting. Okay. So basically you're saying the new wavelength minus the rest wavelength, if that galaxy wasn't moving at all, divided by the rest wavelength. Okay, so Spectrum Calculator. Oh, this is the one where we're actually, this is a set of unshifted and redshifted spectra. Oh, okay. So this would be the unshifted spectra if a galaxy is stationary. It's not moving. So that, in other words, those are the spectra of gases that are studied in the laboratory here on Earth. And we can easily study spectra of gases and know what to expect for gases here on Earth in the laboratory. Then we study the spectra of gases in stars and galaxies. Then we can find out their shift amount. It says each spectrum reflects the dependence of the relative intensity on the wavelength in angstroms. Select the quasar from the drop-down menu located at the lower spectrum. Drag the red vertical line on both plots to calculate the value of the redshift of the selected quasar. Check the value of the wavelength in angstroms for the selected peak in the boxes below each spectrum. The value of the redshift parameter Z is shown in the box at the bottom of the window. Oh, wow, this is huge redshift. So this redshift 4.29, for example, dwarfs this redshift, 0.51. We thought that this is far. That's for the galaxy B000-160, right? But then those ones are huge redshifts. They're over 1. I remember doing one in the last lab or couple labs that where the Z was 1 something and 2 something. So this would dwarf those also, you see? Okay, so now let's see what we would do here. We would look at the quasar. Oh, there's different quasars here. Well, let's just say take a random one. Okay, so we notice these lines in this quasar, magnesium 2. Then we go here, check out the magnesium 2 line. Oh, okay, magnesium 2 line. And that would be the 2845. That's the same one that it should be over here that we just did, 2845. No, that's a little bit off from what we did there, magnesium 2 line. But it should be the same one. So right around there. But it might be that we're focusing on a different magnesium 2 line. Let's see. Yeah, it might be that that's a different one from the one that we had here. This was 2798. and it might have been a different magnesium too. This one, the default one here. So, and this is 2845 right here. Okay, so then we go over here. Oh, wow, that's a huge shift, huh? Okay, that's a shift of 0.6. So then, of course, then you would take a snapshot of that. So that depends on the assignment that's asked here. And then from the Redshift calculator, you put the redshift, and then it gives you the velocity of recession. This is a Redshift. Let's see what it says here. This is the Redshift calculator, which allows to find the velocity of recession v of a quasar in kilometers per second using the known value of the redshift. Enter the value of the redshift into the box to calculate the velocity of recession. Recession means how fast something is moving away from you. Receding. Recede means to go away, to recede in the background. We use that word in English. Something when it's receding, it's furthering its distance from us. Press the reset button to clear the data. Okay, so let's see, and let's go to spectral line exercise. Okay, so they're gonna give us a bunch of quasars. For this exercise, we will determine the distance to several quasars by comparing their spectra with at-rest spectral lines. Using the spectral calculator, first select the observed quasar from the drop-down menu on the lower spectrum graph, and then position the red line so that it lines up directly with the peak line, as indicated in the table below. Then adjust the position of the red line on the upper at-rest spectrum graph to match that same peak. By doing this, the calculator will determine the redshift parameter, record the value of Z from the tool, and use that value in the Redshift calculator to determine the velocity of each quasar. Finally, use the Hubble law to determine the distance to each quasar, assuming a value of H. Okay, so then let's say you just go to one of these quasars, and then you go to the C3 line. So then you just basically would go to choose that quasar, whichever one it is. Then you go to the, let's say, which one was the one that I was pointing to? So let's say the 307. Okay, then you go to the C3 line. Okay, then you go to the C3 line. Then here you go to the C3 line. Okay, then take a snapshot of this, right? And then show your work for how you're getting this. So when you're showing your work, you would actually put this number that shows here, 4208.1, and then you would subtract this number from it, and then divide by, and then show this number again down here. And then you should get the same answer that they're getting. Take a snapshot of this, then show your work, then put in that value here, right? 1.15. Then calculate. Okay, that galaxy is moving away from us at a velocity of 193,286 kilometers per second. Okay, then you take that and you put all that information. So that one, you take a snapshot of that. Then you put that information here. You put the Z that you got. You put the V, and then knowing the V, you divide the V by the H to get the D. Then you put that number here, and then show your work for these 1, 2, 3, 4, 5. But the calculations in this lab, at least so far, are very easy works to show. Just very like subtract, divided, subtract, divided. So that's actually good. So then you've got here quite a lot of snapshots to take of this one here, these, and then this, and then showing the work for the Z's. And of course, the bigger the Z value, the bigger the redshift, the faster the galaxy should be moving, because that means it's farther away. and then the distances should be more. And then submit the answer, and then take a snapshot of that answer as well. Okay, good. Now the expansion of the universe. The expansion described by the Hubble law is not due to the motion of galaxies through space. Instead, it is due to the actual expansion of space itself over time. So this is kind of weird because we also know that galaxies move through space. Some of them move towards us, some of them move away from us, right? But space itself is the one that's also expanding. So it's causing more of them to move away from us than towards us. You see, if space wasn't expanding, some galaxies would come towards us, some galaxies would move away from us, maybe it would be even. But because space itself is expanding, that means a lot more galaxies are moving away from us than are moving towards us. Although a redshift can be related to a recessional velocity, the Hubble expansion is not really a result of all the galaxies moving away from the Milky Way in fixed space. Instead, what is actually happening is that space itself, containing all of the galaxies, are expanding. You see here? So imagine space like a balloon is getting bigger and bigger and causing the galaxies, more of them, to be receiving from us. Likewise, the redshift of spectral lines for a receding distant galaxy is not because the galaxy is moving away from us in space, but rather because the expansion of space stretches the wavelength of electromagnetic radiation traveling between the galaxies to longer wavelengths. You see, so I like the way that they said it. The expansion of space itself, it's like a rubber band. It's stretching the wavelength and causing it to be redshifted. It's making the wavelength larger. And so galaxies that looks like they're moving away from us, that's because space is pushing them outwards. And their spectral lines are redshifted, meaning the lambda prime is larger than their lambda, you see? So universe expander. So this simulation helps you to explore the universe expansion. Use the slider labeled the expansion factor, okay, to adjust the amount by which you want to expand the universe. Click the Connect Dots button to draw the lines between the initial and the corresponding final positions of each galaxy. You can also use the Show Radii button to display a set of concentric circles, space circles, with the center on the observer. So the observer is like right at the center right here. You may set the number of galaxies in the galaxy's input field. Okay, that's good. Click the New Universe button to create a new random universe with another number of galaxies. So this is our chance to be gods, I guess, create our own universes. So expansion factor. Oh, okay. Whoa, I like that. So connect, okay, so let's see here. Galaxies map, Hubble Law Plot. Oh, okay. Connect dots, new universe. Okay, so let's see here, what do we do? Simulation, connect dots. Oh, see that's how much it expanded. Expansion factor. Okay. And then show radii. Okay, show radii. Okay, new universe. Reset. Okay, we're just exploring here now. Select randomly. Hubble law analysis, new universe. This height radii. Okay, let's just see here. So this is, you're starting at a certain point in time, and then you're saying, let's see, what does this one do? Okay, so let's see. Let's show the connect dots, and then let's expand expansion factor 1 to 1.5. Okay, so now I have expansion factor 1, connect dots. Okay, so here's what happened. The expansion went from whatever it was to 1.5. So let's see here, the radii. So I'm changing the center of the observer. I'm basically changing the center, what I'm calling the center. So in other words, there is no particular center to the universe. You can call any person the center, and all the other galaxies look like they're moving away from that person. You see? So it could be that, let's say, the Milky Way is this one right here, and then you can make that the center. Okay, so with respect to us, we're stationary, right? And it looks like all the other galaxies are moving away from us. So you can make any galaxy here the center, then you go back to the original. See, so that becomes the Milky Way. And then you say the further away a galaxy, you see, so if something expands, you see, so then this guy here expands less in the same time. This guy expands a lot more in the same time. You see? So then the Hubble log plot does what? Hubble law analysis. Okay, that's probably we're going to see in the next slide, in the next thing, expanding universe exercise. Okay. Each dot on the universe expander simulation above represents a galaxy. Each dot on the universe expander. The plus sign corresponds to the observer's location. Watch the dots move as you adjust expansion factor to 1.25, click, and then wait, or 1.25, click, and then click the connect dots button, which draws a line between the initial position and its position after the expansion. Next to the galaxy's map is the Hubble analysis table. Fill the rows of the table by clicking on the position of a galaxy before the expansion, black dot, or after the expansion, red dot. Try to select galaxies with a variety of distances from the observer. You may also click the select randomly button to have the simulation randomly choose galaxies for you. When you have filled in the table, plot your data by presenting the Hubble Law Plot button. By pressing the Hubble Law button at the data at the bottom of the table, you will now see a graph of your points and best fit straight line through the data. The slope of this line is Hubble's constant for this space and is given at the top left corner of the graph. Enter this value. So pixels per unit time per decipixels. So in our sense, we're measuring the Hubble constant in units of pixels. The pixels that are on the, you see the recessional velocity pixels per unit time. And then distance is decapixels. So if you go back to this one, in other words, these are all given by pixels on the computer screen. Okay, so let's go back. Let's make the center, this is the Milky Way right here. It's supposed to be the Milky Way. Okay, go. So let's go new universe. Okay, so then go down, make the X the dot. So then hide the lines. Expansion go to 1. Okay, make that the center. It's hard to center it. Okay, connect dots. Okay, then then take a snapshot of this and then go, okay, then go like this. all the way. Did it say the 1.25? Well, we could go all the way to 1.5. I don't think there's a, we can go all the way to 1.5. Okay, then take a snapshot of that. And now we could just take random galaxies from us. So if this is us, we don't think we have expanded, right? So then this guy has expanded from here. Hold on. This guy has expanded from here to here. Distance. Okay, then this guy. Oh, okay. Since that guy was closer to us, see its distance from us. Let's zoom in here to show you what these numbers mean. So this one is the galaxy number, and these are most likely real data. So this, when you click on it, it's going to tell you how far away that is from the Milky Way. You see, so click that. It's galaxy 1599, and its distance from us is 25.82. That's probably megaparsecs. But of course, they're measuring it in pixels on the screen. And then this is because it's traveled more distance in the same amount of time, its velocity is going to be faster, you see. Now this one is farther away, the galaxy. And it also has moved more, you see. So the more space there is between us and that galaxy, because space is the thing that's causing it to expand, the more space there is between us and that galaxy, the more it will expand, and therefore the faster the velocity will be. Okay, then we just start filling up these numbers. I think the order probably doesn't matter. You know, you could do fill out random distances. And so it's plotting their distance and their velocity. And we could probably have the rest do, the computer do it for us, select randomly. So then the graph does it randomly and chooses. Oh no, I didn't like that. When I did randomly, changed it all to long distances. We need data for short distances too. No? Hold on. I think it's probably better if you do it, because select randomly, it's going to choose, you might choose only the far off galaxies. Okay, so then let's go. Okay, so then, so take a picture of this. Okay, so take a picture at the beginning when it hadn't moved. Then you take a picture of this at the end, and then you click. Make sure to get some of the far away ones, like these ones. It's even off the screen, you know, how much they have expanded. Okay, then the middle ones, close nearby ones, and also some from the bottom and some from the top region. Okay, so then you can take a picture. You could also just take a picture of this completed version. So one initially when it was fresh and there were no data here, so that's one snapshot, and then one of the completed this guy with the data showing here, you see. So that would be two snapshots right there. And then we can go to the Hubble Law Map, and you see it's already given the data right there. Hubble Parameter, 4 pixels per unit time per decapixel. So then it's already giving us the slope of that line. It's already giving us the slope. So what you could also do, you see all the lines all the points are on that line. So I want you to select 2 of those points to do a calculation to show how this slope comes out. Right? So then you could just do any random point. So for example, let's say I choose this point, which is 79. Let's see here. What point is that? Recessional velocity. So 70. This is 72. Oh, you know what? Hubble Law analysis velocity. 90. Distance. Oh, it doesn't look like all the data went into that. Hold on. This is 92. 230 distance. The Hubble parameter equals 4 pixels per unit time per decapixel. Mm, 29. Hubble law. Recessional velocity pixels per unit time. Distance is 29. These numbers are not corresponding to these numbers here, decapixels. Probably what happened is that these numbers here are in megaparsecs and these are kilometers per second, but they changed that to decapixels here and pixels. So they converted them somehow in the program, and then they made it into a graph. Okay, you know what? That's fine. So you don't really need to calculate because it's going to be hard for us to calculate this to here because we don't know what conversion the program used. So they're converting from megaparsecs to decapixels, and for velocity they're converting from kilometers per second to pixels per unit time. So we don't know what conversion they're using. Okay, so then based on that conversion, whatever they're using, then they're getting the rise over the run. They're getting the slope of that is 4 pixels per unit time. So when you have filled in the table, plot your data by pressing the Hubble Law Plot button at the bottom of the table. You will now see graph of your points. So then let's see if we did, we put 4 in our case. Incorrect. Note that the units that we have chosen for H in the plot windows are pixels per unit time. A pixel is the smallest element of your computer screen, so it represents the distance as the galaxies in animation move from one pixel to another. A decapixel is 10 pixels. Thus, H has units of a velocity divided by distance. This is somewhat unusual unit is chosen to mimic the somewhat unusual unit of kilometers per second per megaparsec, commonly used for the actual Hubble parameter. Before expression or after expansion. Try to select analysis from a variety of distances. Note that the units that we have chosen for H in the plot window are pixels per unit time per decapixel. Okay, let's see here. 4.00. So let's see if we subtract 90 minus around 10. So this is 90. Rise is about 90 over about 12. So the rise is about 78. 90 minus 12, 78. And then the run is around 24 minus about 3, 21, 78 over 21. Yeah, that's how they're getting the 4. 78 divided by 21. Yeah, it's about 4. So I see how they're getting the 4, but why isn't it allowing us to put 4? What if it's 4.00? It's not letting me put another answer. Try another version. 4.000. There's a little mystery here. What do they want us to put? Note that the units that we have chosen for H in the plot window are, this doesn't, from 1 pixels on decapixels, 10 pixels. Okay. Pixels per unit time per decapixel. And it's going to be decapixels time per decapixel. That one is a mystery because that's what they gave us here. And it looks like it should be around the 4. 70. Let me just do what I think it might be. Let's say 4 is not the number. So 92, around 92 minus 12 is 80. 80, and then this is 23, and this is around 3. 23 minus 3, 80 over 20. Yeah, that is around 4. Slope is around 4. But I can't even do it again. That's fine. Just take a snapshot of that. I'm not really sure. Hopefully it works out with you. Okay, so then you, you have next. The center of the expansion. Although all galaxies are moving away from us because space itself is expanding, it is not possible to talk about the center of expansion or the center of the universe. From the expansion in the previous exercise, it is clear that the plus sign at the center is the center of the expansion. If we assume the plus sign corresponds to our galaxy, does this mean that we are at the center of the universe? In fact, any galaxy will seem to be the center of the expansion for a viewer within that galaxy. Universe expander. Okay, we go back to that universe expander. Okay, so pretty much it's the same universe expander. Universe expansion exercise. We will now perform an analysis similar to the one in the previous exercise, but this time for an observer in a different galaxy. Click the New Universe button on the Universe Expander tool. Set the expansion factor to 1.25 once more. Now adjust the location of the observer by allowing the arrow buttons on the tool to move any galaxy so that the expanded position coincides with its position. This action corresponds to positioning the observer in a different galaxy. You can click Connect Dots, repeat the analysis by clicking on a variety of galaxies, and then do the same thing. Now, it might be that if we set the expansion factor to 1.25, that maybe then the Hubble constant will be different. Hold on, it could be. I'm going to try it again with a expansion factor of 1.25. So now let's move the center to some other point. Okay, new universe, expansion. Wait. Why doesn't it allow me to move it? Click the Connect Dots button to draw. Okay. Hide lines. So it should be moving that X. New universe. Reset. Connect dots. Why isn't it moving? Oh, okay, maybe. Hold on. reset. I did it a while ago. Hold on. Expansion factor 0, reset. This thing doesn't want to cooperate. Hold on. Let's minimize it a bit. New universe. Oh, maybe I click on one of them. Why does that X go there? I did it earlier. I remember. New universe. Show radii. Oh, it has moved. I just didn't see it. Hold on. Oh, okay. New universe. New universe. Okay, so I can make whichever one I want the center, but the X doesn't move with it. Interesting. I thought the X would move with that one. Okay, so let's make this one the center right here. So this is going to be like the Milky Way right here. So I guess what we're trying to find out is, would the Hubble constant change if we make a galaxy, a different galaxy, the center of the universe? You see, does the center make a difference? So then keep it there. But then the expansion factor that you should use for this one should be the same as the one you used for the last one. So if you use 1.5 there, use 1.5 here. If you use, like what they said, 1.25, then use 1.25 here. So make them the same so that we can see if changing the expansion factor changes anything. I mean, sorry, if changing the center changes anything, you see? So then do the same thing now. Go to 1.25. Okay, connect the dots, do your calculation, then take a picture again. Before you did the dots, take a picture, and then also take a picture once you complete the whole table. So again, take some picture from, click some of these ones on this end, and then also click some of the ones here. Okay, and then once you're done, take a picture, then go to the Hubble plot, take a picture of the Hubble plot. So maybe I forgot to mention, we should also take a picture of the Hubble plot in the other one. Oh, so I think it did change the fact that I moved the expansion factor to 1.25. Yeah, it does make sense. In other words, I'm making the universe expand faster or less by changing the expansion factor. What am I saying? I'm changing by the rate at which that universe is expanding. So they're basing their Hubble constant question here based on the expansion factor that you're choosing here. A universe that has a bigger expansion factor is definitely going to have a bigger Hubble constant. So for this one, the expansion factor, it's going to be 2.22. And the previous one should have also been 2.22 if the expansion factor is 1.25. And you should find that the center doesn't make difference, which one you call the center. So then you take a picture of that one, and now let's put 2.22. Voila. You see, it worked. So based on the expansion factor of 1.25, the Hubble constant is 2.22. Wow. And we are done. That lab was quick, easier in terms of calculations, but it helps you to understand a very, very important law of astrophysics. The whole expansion thing, the Hubble law, from which we get the Big Bang Theory and a lot of other important stuff. So you could also look up videos and stuff on it and learn a lot of good stuff from this. Okay, guys, we have one more video left, and that's it. After that, you guys will have learned a lot of good stuff. Bye-bye.